colloquium, uh, and this session, as usual, will be chaired by Dean PRL, Professor D. Palamraju. So I invite Professor D. Palamraju to start.
Very good afternoon. A warm welcome to all of you for the colloquium of PRL, which is being organized as a part of the 4th INSQT workshop. We are extremely delighted to have in the midst of us Professor Genovese as the speaker for today. It is indeed a great pleasure of mine to introduce the speaker. Professor Marco Genovese is currently the research director at the National Meteorology Institute of Italy, or in short, INRIM. He is a member of the Scientific Council of INRIM and is also leading the quantum optics sector, which he co-founded in INRIM. His research works concerns the development of quantum technologies in quantum optics, which have contributed to several applications. These include experimental quantum metrology, imaging and sensing, NV centers, ODMR measurements in neurons, subimaging and sensing, short noise imaging, quantum illumination, quantum enhanced correlation in interferometry, characterization of detectors, sequential weak and protective measurements, quantum reading, and quantum conformance, among many others. Professor Genovese has published over 300 publications, delivered more than 100 invited talks, and chaired and organized several international meetings. Professor Genovese has been the associate editor of Applied Sciences, managing editor of IJQI, and responsible for several projects. He teaches quantum optics for PhD students and quantum communications in the Masters at the Turin Polytechnic University. He's also a member of the Academy of Science of Turin. He's also a member of the Didactic Council of the PhD School in Physics at the university. Today, he'll be delivering the colloquium, Protocols of Quantum Imaging. It is my pleasure to invite Professor Marco Genovese to please deliver the colloquium. I request you all to please put your hands together.
First of all, I would like to thank, maybe you hear me well, or it's better? Is that fine? Okay, first of all, I would like to thank the organizers for having invited me to this very interesting workshop in this very nice place. I always like to come in India. And today I'm going to present you some review about quantum imaging, and why it's interesting. Okay. Yeah. Okay, we are ready. So, but it's not on the screen. Okay, I think we are ready to start. So I was mentioning, I would like just to present an introduction to quantum imaging. What is quantum imaging and why is it interesting? So it's almost unusual to present this part to this audience, but just very rapidly, as we know, peculiar properties of quantum states. We developed the technology for manipulating single photons, single atoms, single ions. So it really became possible to produce technologies exploiting these strange, peculiar properties of quantum states. And now several countries are investing huge amount of funds. I just learned that also India has invested a very big amount of money in quantum technologies with the hope that they will produce breakthrough in our society in the next years. So quantum imaging is one of the quantum technologies. Actually, is the technology that addresses the problem of exploiting the peculiar properties of quantum optical states for improving imaging, for improving the limits of classical optics. There are already several ideas. I will not be able to describe all of them. Here just you see a list. There is in red the theoretical proposal, and as you can see in black, most of these protocols have already been realized experimentally. So we have ranging from ghost imaging, quantum lithography, quantum illumination, quantum enhanced differential interference, contrast microscope, and so on. As I mentioned, I will not able to describe all these topics. For example, I will not discuss the question of super resolution that would require a further seminar. Okay, is there the exigence in the community, of microscopy community, for improving the present method? Indeed, various microscopic techniques are already limited from photosensitivity of the sample, in particular for biological ones, for example, fluorescent microscopy. Others are limited from shot noise, just optical coherence microscopy, photonic force microscopy, and several other techniques. And indeed, on the one hand, the advantage of quantum protocols is usually at very low illumination levels, so it can be used when you have photosensitive samples. And another possibility is to go under the shot noise, because the limit for quantum states is the Heisenberg limit. So shot noises means that your uncertainty is limited by the square root of the number of photons, namely the square root of the intensity. With the Heisenberg scaling, the uncertainty is scaling with the number of photons, namely with the intensity. Okay, so I start with some idea that was already proposed almost 25 years ago by Jonathan Dowling and collaboration, and is to exploit photon number entangled states of this form. Either you have all the photons in one mode, or you have all the photons in the other mode. So these are called Nun states. So what Jonathan Dowling and collaborators demonstrated is that you can exploit this kind of state for improving resolution because the interference fringes are varying with this factor n. And indeed, Yanhua Shi group in Baltimore demonstrated a few years later that this is really the case when you consider a Nun state with n equal 2. You see that your interference fringes passing from direct imaging to coincidence counts have an improvement of a factor of 2 in resolution. So these Nun states have also another very interesting properties, because if you consider an interferometer and you have that the photon can either go in path 0 or in path 1, it acquires a phase difference. And again, the estimation of this phase is as an uncertainty, which is decreasing with the square root of n. This is the just usual scale law. But if you have a Nun state, what happens is that either all the photons are crossing one arm or the other, and so the phase is acquired with a factor n, and now the uncertainty is scaling with 1 over n, so the Heisenberg scaling. So if you would be able to realize this kind of states, you will have a clear advantage in the measurement. And this is true, of course, for photons, but is also true for atoms. And for example, atomic clocks are just atomic interferometers. So in principle, if you can realize systems like these, you would have the same advantage. And indeed, few years ago, okay, few years, it depends on how long you consider few years, but a few years ago, my friend Segeki Takeuchi realized a quantum enhanced differential interference contrast microscope just by exploiting two photon Nun state and demonstrating the quantum advantage with respect to the direct imaging. So this was a direct application of this phase estimation that I've mentioned the slide before. And a little bit more recently, Silberberg demonstrated the advantage again, both for respect to the classical case with the quantum case, both for Nun state in n equal 2 and n equal 3, but n equal 3 only in post-selection. So as you can see, we have proof of principle of the advantage of Nun states, but the number of photons is small, either 2 or 3 in post-selection. So this is a typical situation where you have a very interesting theoretical proposal that maybe in the future will find a real application, but for the moment we are limited by our ignorance how to produce efficiently Nun states with high n value. So of course, in this case, we have proof of principle, but we are not able to pass from proof of principle situation to real application because we cannot have Nun state with a large number of photons in this moment. And of course, if you use post-selection, there are several ideas. Post-selection is the simpler, but if you post-select, all the advantage in having a low intensity is lost because substantially you must use a large intensity and then post-select only the case where you have the Nun state. So there are ideas, but all these ideas are theoretical. So this is an example of a resource, very interesting, but for the moment, not yet ready for real applications. On the other hand, we have a source of photon entangled states that I'm going to describe now. Somebody of the former speaker already mentioned this source. that is really the method that is most used in quantum optical technologies in this moment. That is parametric down conversion. So many of you already know what is parametric down conversion? Raise your hands. Okay. Better to provide some. Okay, I will be fast for the ones who already know, but just what is parametric down conversion? The idea is just you have a higher frequency photons that convert in a nonlinear medium in two photons such that energy and momentum are conserved. So the sum of the frequency of the produced photons is the frequency of the incident photon. The sum of the wave vectors of the produced photons is the wave vector of the incoming photon. Usually you pump this nonlinear crystal with an intense laser because this phenomenon is very weak. So you send milliwatts and you obtain pair of photons. So the conversion efficiency is very, very small. And you have two kinds of PDC. In type 1, both the photons have the same polarization. So they are emitted in circumcentric cone. This is a real picture, ranging from the wavelength of the laser, in this case was in the violet, up to the near infrared when the crystal starts absorbing. In type 2 PDC, the two photons have orthogonal polarization, and due to birefringence, the two Okay, so what I was saying is that since you have this correlation exactly correlation in the transverse wave vector in the far field, it means that you have two correlated points where the number of photons, the Idler signal, are fluctuating exactly in the same way. Okay, this is the ideal situation. Of course, in a real situation, nothing is working exactly like in theory. So the pump is not a plane wave, the crystal has a finite dimension. So this correlation point to point is transformed in a correlation between some speckle. So this is a real picture. So you have a speckle structure, and what happens is that these speckle, which are coherence area, are correlated each other. So when you have a certain number of photons in one speckle, you have the same number of photons in the correlated speckle. And the dimension of the speckles depends on various parameters, the weight of the pump, the wavelength, and so on. So of course, to detect quantum correlation well, the detector size must be larger than the single spatial mode of the single speckle. Okay, these are real pictures. Okay, pictures taken in the lab with or without the interference filter, and you can see clearly this correlation. When you have a bright speckle here, you have a bright speckle here, or you have a dark speckle, you have a dark speckle, and so on. Okay, so how to quantify this correlation? So the idea is to use this noise reduction factor, namely the variance of the difference of the number of photons in the two modes over the total intensity. Of course, in an ideal situation for a twin beam, these two numbers are the same and the noise reduction factor should be 0. One can demonstrate that for coherent states, noise reduction factor is 1. For classical light, let's say super Poissonian light, like the thermal one, the noise reduction factor is larger than 1. But again, this is in an ideal situation. In a realistic situation, you have losses. You have losses in the optical path. Your detector has not a 100% detection efficiency. So you have to consider all the losses in the optical path. And at the end, your noise reduction factor is 1 minus the transmittivity. So if the transmittivity would be 1, you have the noise reduction factor 0. But when this is not the case, the noise reduction factor is approaching 1. Okay, so several groups worked for going to smaller noise reduction factor. In particular, it's interesting to go under 0.5 because at this point, as I will mention, you are in a situation where you can beat in certain schemes every classical optical imaging. So, oh, sorry. We reached this limit, but now let us discuss a few quantum imaging protocols. Let's start with the first example, which is rather famous, ghost imaging. Again, how many of you already know what is ghost imaging? Anybody you know? Right here. Okay, but so what is ghost imaging? Actually, if we wanted to make a small joke, the idea is to take a picture in the wrong direction and to get the image of the object anyway. So it looks, if I say this, it looks a little bit weird. So what is really? The idea is that you have two correlated beams. One is addressed to the object, your ghost, but then for some reason you lose your spatial information. For example, you have a turbulent medium, or you cannot collect the light with a spatial resolving camera. So at the end, you have a bucket detector. So all the light that cross the object or what around the bucket detector is collected in a single piece. So you have completely lost your spatial information. On the other hand, the other beam is addressed to a spatial resolving detector, a CCD camera. Then you correlate the two measurements, and you are able to reconstruct the image of your ghost. Okay, it seems a little bit strange, but I can provide you a classical example how a similar scheme can work. So imagine to have two cannons, and these cannons
are just throwing out balls. One cannon is throwing the balls in a region where you have a bell. The other cannon is throwing balls toward a wall, and they remain glued on the wall. But the two cannons are moving, are just fluctuating. But they are fluctuating in the same way. When one is going right, the other is going right. When one is going left, the other is going left. So every time the ball hits the bell tolls. You hear the ring. And you keep the ball on the wall. If the bell does not toll, you eliminate the ball from the wall. At the end, you reconstruct the image of your bell on the wall, even if the balls addressed to the wall never approach the bell. Okay, so ghost imaging is working somehow in this way. Of course, you can describe mathematically. You can introduce the transfer function, describing your operators in terms of this transfer function, consider your correlation function, you integrate over all the position variable of the bucket detector, because the bucket detector doesn't have spatial information, and what you obtain at the end is that this correlation function, where you have integrated over the spatial variable of the bucket detector, is proportional to the transmission function in the other direction. Okay, so I've got the image. So the first idea of this imaging was proposed by Klushko already several years ago. And then again, Xi group realized with twin beams in '95. But actually, a few years later, both Boyd and Lugiato groups demonstrated that at the end, you don't really need entanglement in this case. If you take thermal light and you split it, you can use the split thermal light for realizing ghost imaging. In this case, technically, there is another quantifier of the correlation, which is called discord. And these are non-zero discord states, but I will not enter in these details. So is really ghost imaging a quantum technique? Is not quantum? Okay, somehow is not that important. If you use entangled states, you have an advantage for a low contrast. When you have a small number of photons per mode, so low illumination level, quantum has a clear advantage. Anyway, it is not evident that you're always in these conditions. Maybe it's not where you are interested to. Okay, then there are ideas for improving ghost imaging, for example, differential ghost imaging, and several other ideas, use of super-thermal light, speckles and vortices for ghost imaging, pinhole quantum ghost imaging. So I will not enter in the details of these. But what I would like to mention is that now there are several proof of principle, and some of the experiments is really approaching an application level. For example, Xi group, not Yanoa Xi, this Xi group, demonstrated the disadvantage in a turbulent atmosphere. You can see as for direct imaging, the turbulence is rapidly destroying your possibility to reconstruct the image. This does not happen for ghost imaging. Ron Meyers at the Air Force, US Air Force labs, demonstrated the imaging through a diffusive media. Don't worry, this is not a real soldier, it's just a toy, just for demonstration. Or we demonstrated that you can make Faraday imaging of magnetic domain inside the cryostat. Of course, it's difficult to have a CCD camera inside the cryostat. It's much easier to collect the light with an optical fiber, and so on. Okay, so ghost imaging is a first technique that can have interest. Of course, the imaging through a turbulent medium can find application in space. You know, for example, through when you can make imaging through a Earth atmosphere or any other atmosphere. Another technique that I mentioned very, very rapidly is correlation planoptic imaging that was developed in Bari. You know that planoptic imaging is a classic technique where you have micro lenses before the camera. And so thanks to these micro lenses, you acquire information about the wave vector, and this allows you to reconstruct the image even out of focus. So you have a very field depth, very big field depth. So the idea of Bari group is to split by exploiting correlated light, the micro lens part, and the direct imaging to improve it. Actually, this can be done eventually with thermal split light or with twin beams. And very recently, we have a correlated ghost imaging with a planotic imaging. So obtaining a ghost imaging where you have a very good depth of field, you can see respect to the classical ghost imaging where you lose the image, where you are out of focus, you keep the possibility to reconstruct the image even where you are clearly out of focus with the classical technique. Now, a second technique that I would like to mention a little bit more in detail is a technique that was initially developed by Zeilinger group. And if I'm not wrong, there is some poster describing those progresses in this sense, isn't it? Who is the author? Okay, so I'm introducing your poster, so maybe if it will be useful, maybe not, but okay, what is quantum imaging with undetected photons? Okay, so the idea again is to exploit this parametric down conversion phenomenon. So you produce in the first crystal two correlated beams. Okay, so you have split the pump beam. One is producing in this crystal two correlated beams. Eventually, the two beams can have a very different wavelength. You know, maybe one is in the middle infrared, the other is in the visible light, and this can be a point of interest. You addressed one of the beam to the object to be imaged, but then you do not send it to a camera, but you readdress this beam together with the pump to a second nonlinear crystal, where again I produce two correlated beams. So this now is a stimulated emission, and the image has less the print on this beam that now is leaving the print on the correlated beam in the second crystal. Then you make a correlated measurement of the light in the visible region produced in the first crystal that never crossed the object, of the light in the visible wavelength produced in the second crystal that never crossed the object, but by correlation you are able to reconstruct the image. Because substantially this beam that eventually is in the middle infrared where you don't have good cameras has left a print of it in this second crystal when producing the correlated beam. Okay, so after this first proof of principle, there were a lot of development. Here is just a few papers of Grefe, Phillips, Ma, and Zeilinger for imaging, Masha Chekova for spectroscopy. Here you can see a paper of Reimelov that allowed to make an image of a mouse art in the infrared by exploiting this technique. So this is a rather interesting technique that can have significant application, and a lot of people is working in this direction. A similar technique is this one developed by Boyer and others, Boyer-Lett and others. The idea is just to have the object in a seed before a single crystal, and then you have a stimulated emission in this crystal. So at the end, you have a correlated image in the other correlated beam produced by this phenomenon. So it's just a simplified version of the other one. Okay, now I'm arriving to another technique, which is subshot noise imaging. So which is the idea of subshot noise imaging? Again, the idea is I produce twin beams. One beam is addressed to an object to be imaged, but this object is very, very weakly absorbing. Maybe in our case was just a few atomic deposition on a glass. And so the absorption coefficient is small, and you don't want to illuminate it too much because it's photosensitive. So at some point, the image is lost in the noise. What Lugiato and others and Como proposed is to exploit the properties of twin beams, since the noise is strictly correlated, you remember. They are fluctuating like a thermal beam, but they are fluctuating together, exactly in the same way. So I measure the noise on the reference beam, I subtract the noise from the other beam, and in the ideal situation, I completely eliminate it. Actually, of course, in an experiment, you never have an ideal situation. I mentioned you have losses, so your noise reduction factor is not 0. But if you can keep your noise reduction factor under 0.5, you can demonstrate that no classical scheme can beat the quantum one. So you have for sure a quantum advantage. And indeed, we realized this first proof of principle again a few years ago, almost a few years ago. And here are, we were just imaging a few atomic layers deposition representing a pi. And you can see that with classical imaging, it was substantially impossible to recognize this object, while with our subshot noise technique, this was possible. So, of course, you can quantify the advantage, but I will do later for a better scheme. So this was just a proof of principle. At the time, the number of pixels was small, the resolution was small, the noise reduction factor was under 0.5, but not largely under 0.5. So since then, of course, this is not interesting for real application. We know that biologists, for example, are really interested in having a wide-field microscope at low illumination level for several reasons. But for this reason, you have to improve that proof of principle experiment passing from 70 pixels to thousands of pixels. And it means that you must have thousands of correlated modes of light. And you have to enhance the signal to noise ratio. The advantage should be significant, not just the one of a proof of principle. And you must have a good resolution, smaller than 1 micrometer. Otherwise, it's not competitive with classical microscopes. And indeed, we realized these microscopes again a few years ago. And of course, the problem is the trade-off between having several pixels and having a good resolution, but keeping a good signal to noise ratio. So limiting losses and having very good correlations among modes. So, okay, this is the results. You can see again an image of the position, in this case representing a phi, is evident advantage with respect to the classical scheme, and this can be quantified, and you can see the advantage. Of course, smaller resolution, larger advantage you can have, but there are, for reasonable resolution, you still have an advantage. And actually, you can have some optimization of the subtraction of the noise, and these increase again the advantage even more. And so we arrive to this. Oops, sorry. Let me see. Okay, this is the first quantum movie. So this is just a moving object that we are just imaging with a CCD. Okay, it's a very good CCD camera. And you can see these are just very fast acquisitions, smaller than 100 microseconds, and of a very low illumination level. And this is the case where usually you have a quantum advantage, when you are a low illumination level. But if you want to have fast imaging of an object that cannot be irradiated with a lot of light, because otherwise you will damage it, like biological samples, this technique can become significant. So here is the quantum, and here is the classical case. Okay, so after this first proof of principle, now Again, also this technique, there are several groups working in this direction. For example, a rarity group realizes a raster scanning microscope. So in this case, it doesn't have several modes correlated at the same time, so it cannot realize wide field microscopy, but it scans the object with a single mode. So it cannot be fast, but if you don't have the need to be fast because your sample is not something changing in time, you can take all the time you need, and of course in this way you can have a very, very good signal to noise ratio because you are using a single mode. So you work a lot on having a good single mode. And these are images with the usual NIST reference demonstrating the resolution of the method. Again, similarly, this group realized a raster scanning of a biological sample, and here is another scheme, always single mode and so on. So the work in this direction is going on. On the other hand, we decided to realize phase imaging subshot noise. You know that a microscope, when you are trying to make microscopy of a very weak absorbing object, at some point, what is convenient to do is to use a so-called phase microscope. So what you are measuring is the phase introduced by the sample on your optical beam. This is a technique that is rather exploited in biology. So the idea is that you have your intensity and you can reconstruct the phase just by looking to the derivative of the intensity when you have a small defocusing of the sample. And of course, also here you introduce some optimization, but this is not important, for the subtraction of the noise. Again, so the scheme is very similar to the previous one, but now is in phase imaging instead of absorption imaging. So you have your reference beam, you measure the noise in one beam, and you subtract to your other branch where you are making phase imaging. And you can see, as again, you have this famigerate pi that is reconstructed with the quantum phase imaging respect to a classical one when you cannot see it. Also, we have this lattice, and you can see the reconstruction. You can quantify your advantage. And, okay, but time is running, so I will not enter into the detail, but you see there is always a clear advantage of the quantum scheme. Okay, so another protocol that is receiving a certain interest, we have already discussed during lunch and dinner with some of you, is the so-called quantum illumination. So what is quantum illumination? The idea is just, I have a probe, this probe is addressed to a target, and I wanted to identify if the target is present or not, but the light coming back. It seems pretty simple, no? It's like a radar. But then, of course, you have noise. You have environmental noise. Eventually, some noise can be introduced for hiding the target. And at some point, you are unable to understand if the light that is coming back is reflected by the target or is just noise. In particular, when you want to remain undetected and you cannot send a huge amount of light, but you want to send a weak field, it is particularly difficult to beat the noise. What Seth Lloyd demonstrated a few years ago is that if you exploit entanglement, you have an exponential advantage. Okay, so this was the paper of Seth Lloyd, again a few years ago, published on Science. And what is interesting, okay, Seth Lloyd didn't say anything about how the state should be, how the measurement should be. He just used Elstrom bound and said, okay, this is the limit for quantum state, entangled quantum states, and is beating exponentially the classical scheme. So you have an exponential advantage. No, now exponential is used, abused, but it means that it's really a huge advantage. And again, this scheme, what is interesting in this scheme is that usually when you have a quantum scheme, quantum protocol, all the quantum protocols are very sensitive to losses and noise. Now you have entangled states. As soon as you have losses, your entanglement is deteriorated and the quantum scheme is losing its advantage. What is interesting of this original proposal of Seth Lloyd is that this scheme is extremely robust against noise and losses. So it's one of the few quantum protocols that continue to have the advantage, even if the entanglement, when you include also this noise, is lost, you have the advantage because you make correlation measurements. And so you are able to eliminate the noise in this way. Of course, this can have various applications, then we will discuss them better. But if you want that this interesting theoretical proposal real find application, you must demonstrate that you are able to use it. It's like we had this first example of null states, very interesting, but at the moment nobody is able to produce null state with IN. It's possible to realize this quantum illumination with reasonable tools. Okay, so again, Seth Lloyd, together with several other people like Shapiro, Pirandola, Maccone, Giovannetti, etc., introduced the idea to use twin beams, the famous twin beams that I'm talking about them since most of my seminar, as a resource. And they also introduce a strategy for measurement. Unluckily, that strategy was not that simple to be realized, but they demonstrated that still you have an exponential enhancement. Again, is extremely robust against noise and losses. Okay, so maybe there is some possibility to do it. And indeed, what we have decided to do, okay, let's use twin beams. We have twin beams in the lab, but also let's choose the simplest measurement strategy. Just measure correlation between the beams that has been addressed and the reflected back and the reference beam. And again, we have demonstrated that if you don't have information about the noise and you have an exponential enhancement with respect to the classical scheme, and you keep the robustness against noise and losses. So we realized this proof of principle experiment with twin beams, and you can see that here is just what happens for the classical target detection when the noise is growing. Here is the probability of error. You see that very rapidly you have a 50% probability of error. It means you can throw it, a coin is the same. But for the quantum light, even at relatively large noise, please notice the scale is logarithmic. So you have still a clear advantage. And this is a clear exponential advantage. So quantum illumination has attracted a lot of interest. There were then papers discussing which is the real resource and relevant for this experiment. There was an improved detection scheme using homodyne detection of a Shapiro group that was applied to a secure quantum communication. There are ideas for extending to microwave region. Of course, if you can realize in microwave, you are going toward a radar, a real radar. But here also there is some first proof of principle demonstration, but microwaves, of course, it's difficult to produce entangled states, but even more difficult, you cannot measure the single photon of a microwave, of course. So it's really possible to build a quantum radar. It's not at all evident. A quantum LiDAR, probably yes. And of course, there is also interest in going toward X-ray detection, where of course you must have the lowest possible dose when you make imaging, because X-ray are deteriorating almost everything. And we are also now starting to look if it's possible to use a quantum LiDAR, for example, for satellite detection by using a 1 meter class telescope on ground and we are working in this direction. Okay, then maybe I will try to go a little bit fast because time is running. I just mentioned very rapidly other protocols where twin beams can find interesting applications. For example, Stefano Pirandola proposed that they can have an advantage in reading a classical digital memory. So if you have your bits, classical bits, which are 0 and 1, and it depends on the reflection or absorption. What Pirandola demonstrated is that when this absorption is not very different, you can have a clear advantage by exploiting twin beams. And again, we demonstrated in the proof of principle experiment this theoretical idea. You can try to test, for example, if you have a channel and this channel is described by some, of course, quantum operation, and you want to recognize if this quantum operation corresponds to what should be, so it's conform to some standard, and you exploit again twin beams, you can demonstrate that you have an advantage in this case. Okay, so I'm trying to arrive to the conclusion for leaving some space for the discussion. So what I hope to have, at least the take-home message that I hope to have transmitted to you is that actually among quantum technologies, quantum imaging has several interesting possible applications, and also some of the protocols is now substantially ready for real applications. And so maybe in the next years, some of these microscopes will find a real use, for example, for biological samples. Others are more far from a immediate application, but they have interesting potentialities. So thank you for your attention.
Thank you, Professor Genovese, for this exciting talk with several applications and several experiments that have been done. It's, again, being from people out of the field, it was a great exposition for you. Thank you very much. But I'm sure there will be questions for people who are in the field.
Or not in the field, let's say.
Or out of the field.
Nice talk.
Thank you.
So you see, the ideal results you are showing about these undetected photons and then seeing their images. So similar kind of protocols have been used for classical light, like image up conversion kind of techniques people are doing. So use of this undetected photon going to the single photon level, which is difficult. What is the advantage they get when they're using a single photon as compared to the classical light and doing the image?
You mean this undetected?
Yes.
Okay, as I mentioned, usually quantum protocols are interesting when you must have a low illumination level. It's not evident should be single photon, maybe a low photon number twin beam, or in the case of undetected photons, these stimulated beams with a low average photon number. The advantage, the real advantage is when you are interested in low illumination level. When you are interested in low illumination level, actually when your sample is photosensitive. Or for example, as I mentioned, maybe you wanted to make a sequence of a biological system which is evolving. So you must make several images in a short time, and you can send watts of light over the cell, otherwise either you kill it or at least you modify the process. So in these cases, to have an advantage of this kind can be relevant.
You see, stars, they have record image the stars in the infrared light or deep infrared light through the image conversion. So there are papers where people have used of stars where light is very faint, but still they have the star with very huge light, taking that starlight and mixing with bright form photo and converting it to a particular wavelength, which is technologically not so challenging, which is consistent. So Prof has done that also. I don't know basically with this kind of protocol where
how do compare the two protocols? Actually, as I mentioned, I am not the author of these papers. I was just describing the work of other groups. But I think that the image I've shown at some point, for example, of this mouse heart, has a very good resolution. And here, the problem, of course, is the mode matching in both cases. And I'm not sure, I never saw anything like this with this second harmonic generation. So I think this technique has advantages in this direction. But there is the poster, so you can ask everything.
Yeah, it was a very nice talk with a lot of stuff from the for review. Just a quick question regarding your quantum movie that you had, the microscopy.
Yeah.
How exactly you're doing the detection there? That part I didn't get.
Okay, this one, the question is?
Question is, how exactly you do the detection in the microscopy, how the detection scheme works? If you can
okay, the microscope is substantially this one. So we have a CCD camera at the end with a very low noise. So this is the imaging scheme, the imaging scheme. And we were making acquisitions shorter than 100 milliseconds. And the illumination level was, okay, now is not mentioned, but was very, very small, so less than microwatts.
Okay.
Thank you for a wonderful talk. So I have a question regarding quantum illumination actually. So you were talking, just one thing I would like to know whether you are just talking about intensity correlation or photon number correlation when you want to get the advantage. Because the issue is because if I understand the quantum illumination is, they are showing that it shows advantage when there is a lot of background noise actually, even more than your signal actually. So I'm not able to digest how, if background signal is more than what is my twin photons, how I'm able to get the quantum advantage.
Actually, because the background is uncorrelated from the other beam. So when you measure the correlation function, is not.
There could be accidental counts also, right? So
it can be the accidental counts, but of course you have to consider that. Okay, you have a very large background, but here you have a good correlation in wavelength, good correlation in time, at least if you know the distance or you move your time window, and you can filter most of the background out in this way, and at the end you can really find this kind of advantage. I can provide you the mathematics, of course. Our scheme is not optimal. Our detection scheme is suboptimal. But of course, you can move toward the optimal schemes where of course, the mathematical demonstration is more rigorous, but from a practical point of view, it's not evident that this is what you want to do. So,
yeah, thank
you. Thanks a lot. I think I also had similar question, but it's still, so what kind of correlation do you use? Is it always intensity correlation or phase correlation?
Okay, in our scheme is on intensity. Of course, if you want to have an optimal scheme, you must use also phase.
I also have a question. So you talk most of the time about noises. So And if I know it, that most of these experiments usually done in the dark conditions, so is it always the environmental noises, or is the source itself has some noises, which also needs to be taken care of to generate such images?
Okay, the relevance of noise depends on the scheme. So, are you considering a specific scheme in this moment?
For example, ghost imaging.
Ghost imaging. Okay, again, ghost imaging, what you are making is correlation, and this, of course, is sensitive to noise, but again, you can filter in wavelength, you can filter in time, so at the end you can reduce the noise. And for example, let's consider quantum cryptography. You can make quantum cryptography at single photon level during the day. Why? Because you are filtering out all this huge noise. And for this kind of imaging, since you know very well the wavelength, you know the timing, you can do something similar.
Okay. Thanks again for the beautiful talk. I want to ask something. I don't know if there is an answer directly. Going back to the discussion of Hanbury-Brown twist, when the classical correlation was not explaining everything, and then Glauber came in with the quantum correlation. Now, what you mentioned that in the imaging, specifically low light level, you have quantum advantage, whereas with the high intensity level, even a random classical light could be good enough, right? Is it something that they are in the correlation itself, the correlation, the way it is measured, uh, quantum statistics is equivalent to classical statistics? The only thing is that at low light level, you are getting the advantage because there is no light. Now you have few photons. You are getting the advantage of this, the randomness in the quantum randomness that is inbuilt in quantum source.
Let's say more than the point is that usually when you can increase arbitrarily your intensity, why to use a complicated scheme like a quantum light? You simply increase the intensity as much as you want up to when you have a good image. So if you increase the twin beams intensity, it's true that for the single mode, the thermal is going toward Poissonian. But this doesn't matter, because what is important for you are the correlations. So if you have a very intense twin beam, for most of this scheme, at the same illumination level, you have always an advantage with respect to the classical one. The point is that it's not that easy to have a very intense twin beam. And then if I can increase arbitrarily the illumination level, I say, okay, I increase again the classical light and I beat the quantum scheme. Of course, you cannot increase arbitrarily the illumination level, because at some point you burn everything. But
no, I want to know your thought on the randomness. Quantum randomness has some equivalence with classical randomness, and is that what is playing the role in terms of low light level versus
classical and quantum? What do you mean? The statistics of the beams is different.
Yeah.
Usually, quantum light is sub-Poissonian.
Yeah.
Classical light is super Poissonian. But for example, for super resolution, you have this classical method of super resolution, which are exploiting the fact that the light is super Poissonian. Or you can exploit single photon emitters and the properties that the light is sub-Poissonian. In both cases, you obtain super resolution that you don't have when it is Poissonian. So the properties of light is, in some cases, the fact to have a quantum light is not evident is a clear advantage, or you have a similar technique with classical light. In other cases, like this photon subtraction, you cannot do with classical light. This requires entanglement, and entanglement is.
Thank you.
So thanks for this very nice talk. I have a question. So I think most of the methods you described are based on correlations between the signal enabler and the photon number basis.
Yeah.
But there is another alternative, which is to use the squeezing of one of the quantities of the field.
As I mentioned, I cannot describe all these methods.
No, but I'm sure.
I'm limited to this.
I just want to have your.
Yes, no, of course, squeeze light is another very interesting possibility for realizing quantum protocol. Of course, the first protocol of quantum metrology is the idea of caves, of using squeeze light in interferometer. And now this is applied to Virgo and LIGO, etc. So of course, squeeze light is another tool, but it depends on what you want to do. I have to limit my, if I had also introduced squeeze light, of course, this is another possible colloquium probably.
Thank you.
Nice talk. I'm from Rockfield. So I just wanted to know about this undetected photon discussion you were doing. It was carrying out at night. So can also be like using the same technique, we can also use virtual photons instead of undetected photons, which are real.
Excuse me. Use.
So when you say undetected photons,
yes,
they must be real photons, right?
Yeah.
So if we
virtual.
Real photons.
Yeah, and your question if I can use virtual photons.
So virtual photons, so to get the similar kind of information.
Yeah, but I don't have any clear idea how to correlate. Yeah, the point here is the correlation. How should you have a correlation?
If you consider, field theory.
Yeah, no, I know that you can have virtual photons, but you should have a correlation, entanglement between virtual and real photons, because the other must be real, the one you measure. And
can you also get some information indirectly? I mean, it may not be directly, some indirect way.
In principle, yes, but I don't have any idea in this moment how you can do it.
Thank you.
Yeah.
The virtual photon comment is there are entangled sources. I mean, there are theoretical papers, of course. You can have entanglement with vacuum.
Yeah, no, I know.
Right?
I know, but in this case, there are two virtual photons.
Right. Say, for example, your noon state that you're mentioning. I mean, it's it's entangled with the vacuum.
No, in quantum field theory, the vacuum is an entangled state, and you can create virtual photons. But when you measure one photon, this is becoming real. And so also the other should become real, because otherwise it's... and you must have energy pumping somehow, because otherwise you are violating conservation. This is the point. I cannot imagine to keep one photon virtual and the other real.
So you have been working in quantum radars. So what is the latest, like maximum advantage, 3 dB, 2 dB, 4 dB, when you are using this quantum illumination? What is the latest?
For what? For squeeze light?
Any light in quantum illumination.
In quantum illumination. Actually, it's not much quantified in terms of dBs.
Compared to coherent detection, what is the advantage? Generally, they are not getting much advantage compared to...
No, okay, I have to say that the quantum illumination, for the optical light, for the moment, we have proof of principle experiments. So now the real point here to pass from proof of principle to real applications. So when we will start to go to real application, of course, this will be important. How many dBs advantage I have. But for the moment, the advantage was the one I shown you. is not yet in terms of dBs. We quantify in terms of probability of error. Okay, so you can see that for example, 10,000 background photons, the probability of error of the classical scheme is 0.5, while here is 0.2. But if you go to 5,000, here is at least 5 times smaller, and so on. So
Okay.
Any more questions? Yes.
Very nice talk. I have a question related to the radar one. Is there any experiment that you'd like to thermal light for? You have LiDAR, but instead of like laser, if you use thermal light, is it advantageous?
for LiDAR.
Can you do some kind of ghost imaging?
So you means the long-range ghost imaging, actually. As far as I know, there are several proposals, but no real experiment on a long base.
Okay. Any more questions? Any question online? No. Okay. Thank you, Professor Genovese.
Thank you very much for attention.
Excellent talk. For really exposing various applications and introducing the topic and also having answered so many questions. Thank you very much.
Thank you.
If you could please stand here, as a token of our love and appreciation, we would like to present you something. Request the organizers to announce the next, whatever is the program.
Now we are going to have poster session. I think